I believe consciousness involves the collapse of the wave function. The physics involved in conscious thinking has to be non-computable physics.
You think we need uncomputable physics just so that I can sit down and write an essay that has reasoning in it?
My view is that yes, it is non-computable. And that somehow nature has been clever enough to produce beings which can tap into the non-computable aspect of the physics.
Penrose, you're doing it the hard way. There's easier ways to get this stuff done. You can just use neurons that propagate weights according to computable laws.
Gödel's theorem I found stunning. The whole point about the Gödel theorem is how do you transcend the rules? And that's what you do, by understanding them.
Whoa, man, slow your roll. That is such an overblowing of Gödel's theorem.
I don't understand why AI cannot create its own rules.
Because it doesn't know that they're true. Knowing why they're true means you understand them. What does understand mean? You've got to be conscious of them. Consciousness enables you to transcend the rules.
I think Penrose is way off base, like not even close to making a coherent argument. Welcome to Doom Debates. Roger Penrose is a Nobel Prize winner and one of the most famous and productive physicists alive today. I'll just read you some of the accomplishments he's known for. Singularity theorems. His revolutionary work with Stephen Hawking proved that singularities, points where spacetime breaks down, must exist under general relativity, fundamentally changing our understanding of black holes and the Big Bang. Okay, he's known for Penrose diagrams, conformal diagrams that allow visualization of the causal structure of spacetime, becoming essential tools in relativity and cosmology. He's known for twistor theory, a mathematical framework attempting to unify quantum mechanics and relativity, which continues to influence theoretical physics. He's known for Penrose tilings, non-repeating tile patterns that exhibit five-fold symmetry, previously thought mathematically impossible. These aperiodic tilings later found connections to quasi-crystals in material science. Okay, that's just a little sample of all the stuff he's done over his long and storied career. Today we're going to be examining his AI views, which honestly are pretty Looney Tunes. And he's developed a reputation over many decades for having very unique fringe views on the whole intelligence and AI situation. So it's going to be interesting to cover. It's not really a serious part of the AI debate happening today. It's really off in the fringe. But Dr. Penrose is just such a freaking genius that it's just interesting to unpack what is his worldview. How can he just be so wrong off in his own world? What exactly is it that he's wrong about? Why is he wrong? It's still interesting that he's getting interviewed and he's giving us a chance to peer into his worldview because after all, he is extremely intelligent. So there's got to be something to learn. Now, what is that worldview? What does Roger Penrose think about intelligence? Well, there's so many pieces to this that I want to make sure I give you a good overview, so let me read you what Claude says. The core of Penrose's theory is that consciousness is not merely computational or algorithmic. In his books, particularly The Emperor's New Mind, 1989, and Shadows of the Mind, 1994, he argues that human understanding and consciousness involve non-computational elements that cannot be replicated by classical computing systems. Key aspects of Penrose's views include 1. Quantum mechanics and consciousness. Penrose proposes that quantum processes in the brain, specifically in structures called microtubules within neurons, play a crucial role in generating consciousness. This theory, developed further with anesthesiologist Stuart Hameroff, is known as orchestrated objective reduction. Aspect number 2 of Penrose's views is Gödel's incompleteness theorems. Penrose draws on these mathematical theorems to argue that human mathematical understanding transcends algorithmic processes. He suggests that our ability to recognize mathematical truths that formal systems cannot prove demonstrates that human cognition isn't purely computational. Aspect number 3 of Penrose's worldview, non-algorithmic processing. He believes that the human mind can perform certain kinds of understanding and insight that are fundamentally beyond what any algorithm can accomplish, including quantum computers or neural networks. And aspect number 4 of Penrose's worldview is physical collapse of quantum states. In his orchestrated objective reduction theory, consciousness emerges from the collapse of quantum superpositions and brain microtubules, which Penrose suggests happens according to a specific interpretation of quantum gravity. So those are the 4 aspects of his worldview. Like I said, pretty unique. I haven't really seen anybody else make these claims. And then Claude finishes off, Penrose's views remain controversial within both neuroscience and philosophy of mind, with many scientists critiquing both the theoretical foundations and the lack of empirical evidence for quantum effects being relevant at the biological scale of neurons. Nevertheless, his work represents one of the more mathematically sophisticated attempts to address the hard problem of consciousness. Okay, Claude, well, that's very polite of you. I personally did not find much merit whatsoever in any of his claims. I'm stunned that he continues to make these kind of claims, frankly, but I think you're going to find this is a fun episode. I explain Gödel's theorem and what I think are the implications of it and how it's night and day different from what Penrose thinks. I explain how I think Penrose is actually clowning himself, and you could make a lot of the same arguments against him that he makes against algorithms. So sit tight. I think this episode will be worth your time. Let's dive in.
A few times you talk about the Nobel Prize in physics for fathers of AI, Nobel Prize in chemistry, Sir Demis Hassabis, co-founder of DeepMind, that's AI system, David Baker, computer vision, digitalization of proteins. Don't you think there's a tribute for AI?
I see. Well, you have to be careful. First of all, the name is wrong. It's not artificial intelligence. It's not intelligence. Intelligence would involve consciousness. And I've always been the strong promoter of the idea that these devices are not conscious. And they will not be conscious unless they bring in some other ideas.
But intelligence, it's not consciousness.
It depends on consciousness. You see, well, it depends on how you use the word. I think when people use the word intelligence, they mean something which is conscious. I mean that.
Penrose is coming out the gate saying we can dismiss all of today's artificial intelligence as not being intelligent because it's not conscious, and consciousness is required for intelligence. Couple things to unpack there. Number 1, how do you know it's not conscious? A lot of us suspect that there's a little bit of consciousness in there, even if we don't understand how conscious, maybe just less conscious than an ant, maybe as conscious as a cow. Nobody really knows. Penrose might say, I know, because consciousness requires quantum microtubules, and we know that the hardware of AI doesn't have that, so it's almost certainly not conscious. So he's got an ace in the hole where he can answer this consciousness question by referring to a secret ingredient. So he's not even a functionalist about what it requires to be conscious. So he's got quite a worldview where he can say, it doesn't have the secret ingredient of quantum microtubules, so it's not conscious, and then it doesn't have the secret ingredient of consciousness, so it's not intelligent. Checkmate. Must be nice to be Penrose, where you can just boil everything down to not having a secret ingredient, so you can confidently say that something is not consciousness and therefore not intelligence. It's a nice little position to have. Of course, the secret ingredient in reality is impotent. Quantum microtubules aren't actually the source of intelligence or the source of any power whatsoever. The second thing I want to point out about how easily Penrose thinks he's dismissing artificial intelligence, I want to point out that this is an example of arguing by definition. If you search my YouTube channel archives, I have a video about why it's actually very weak to argue by definition. Penrose is like, look, I know the definition of intelligence. It's tightly linked to the secret ingredient of consciousness and quantum collapse. And because AI doesn't satisfy my definition, therefore it's not truly intelligent. It's not truly artificially intelligent. And so let's dismiss it. But hold on a second. When we're talking about the real world, we're talking about questions like, is the AI going to get very powerful? So when Penrose is dismissing it, is he dismissing the idea that it's going to get very powerful? Is there any predictive power in the way he points out that artificial intelligence doesn't satisfy his preferred definition? Is the failure to satisfy that definition linked to a prediction about limits on AI? Because when I hear Penrose talk, it kind of implies that AI isn't about to disempower humanity. It kind of implies, oh, it's not even intelligent. To me, that has the connotation of, well, we're probably safe then. But the connotation isn't the same as the point he's making. If the point he's making is just that it doesn't satisfy his definition, he hasn't addressed the possibility that something not satisfying his definition is still going to disempower humanity. So my question is, does Penrose explicitly actually predict that AI isn't about to overtake humanity, disempower humanity, be much smarter for practical purposes than humanity? So in Penrose's worldview, shouldn't it be possible that something that isn't intelligent nevertheless does every job better than human and disempowers humanity? So that's what I want to ask Penrose about is, okay, fine, cast definitions aside, let's not talk about intelligence, let's just talk about powers that an agent can have. And does he think that AI is on track to have more and more powers? Or if he thinks something is missing in AI that humans have, how does that translate to a prediction about AIs not being able to replace humans in various specific functions? Will AIs never be able to write as well as humans? Because that seems to be getting very, very close. And would he have predicted that AIs would have gotten as far as they did? I don't know. It just seems like Penrose is very much attached to a semantic argument, and he's missing the empirical discussion about what AI is actually able to do, regardless of how he wants to define his terms. This is a very common failure mode. Like I said, I made a video about it, about why it's not a good idea to argue by definition. And referring to definitions is also a move that the David Deutschians make, right? They bust out, true creativity. You cannot define true creativity. Therefore, AI is not truly creative because all it does is follow rules. So they bust out this kind of word thinking, this argument by definition. And then they miss the idea that AI is getting more and more powerful and it's breaking every barrier, every specific barrier that they can think of. So there's a little bit of a connection there between Penrose and the Deutschians.
These devices are not conscious, and they will not be conscious unless they bring in some other ideas. They're all computable notions.
There's another Penrose keyword, computable. And he means this in the technical sense of computability theory. So in Penrose's worldview, and this is a very strange, unique worldview, not many people share it, but in Penrose's worldview, what the human brain is doing to be conscious and intelligent involves quantum effects in the microtubules of our neurons, which cause the input-output behavior of the human brain to be uncomputable. So no formal specification whatsoever, even if you had the perfect bit string to specify the current state of a human brain. In Penrose's worldview, it doesn't matter because the physics transcend computable physics. Something uncomputable is happening in the universe. When humans do what humans do and we exhibit intelligent behavior and conscious behavior, something uncomputable is happening. So there's just no possible algorithm you can write in principle. You just need a totally different hardware. You need uncomputable hardware. You need uncomputable laws of physics to power the uncomputable hardware. And in fact, our physics is doing that in his view. And so that's why he's coming right out and saying, oh, today's AIs, they're computable. Let's contrast that to my worldview. My worldview is all about the difficulty of search. For example, take math. You could prove anything interesting in math, anything that has a reasonably sized proof. You could, in principle, prove it if you just had a lot of time to search. If you just had 10 to the power of a million seconds to search, you really could find any possible proof of 1,000,000 characters or less of anything that's true if you just had 10 to the power of a million seconds to search. You would just go check every possible proof, and then you'd come back and you'd be like, hey, here's all the proofs that are correct. And as a result of that, here is all the short statements with reasonable length proofs that are correct. Think about all the gnarly statements in math that have resisted proof for centuries. You know, like the Collatz conjecture, where you take any number, you multiply it by 3 and add 1. You divide by 2, keep dividing by 2 until it's odd, multiply by 3 and then add 1. Yeah, it's a fun one, the Collatz conjecture. That's an example of something that number theorists are really struggling with, and they have been for hundreds of years. Well, if you could just search every reasonable length proof, the correct proof of that conjecture being either true or false would just fall right out. The only problem is the size of the search space. I feel like a lot of commentators on AI, when they talk about like, oh my God, you need true creativity, you need quantum microtubules, they just don't appreciate this perspective of like, a lot of things are trivial if you have exponential speed search or, hyper exponential search. A lot of things become trivial. And so the whole name of the game is, can you search efficiently, or can you take shortcuts in the search space? That's all creativity is. It's such a hard problem to be able to cut through a search space that if you can do it, congratulations, you're truly creative. You don't need an additional secret ingredient besides just the input-output relationship of being able to cut through really large search spaces. If you can do that, you can be the greatest, most insightful mathematician there ever was because you can cut down the proof space to this beautiful proof. Like whoever finally proves the Collatz conjecture one way or the other is equivalent to just somebody who's really good at searching the space of proofs. It just takes time, it takes computation steps. So if you just throw a lot of computation steps at the problem, if you have a universe that embeds our universe and it's exponentially bigger than our universe, well, within that universe, their computers can just plop out all the proofs of the Millennium Prize problems, assuming that reasonable size proofs exist. So there's another gotcha. You could be like, oh, there's a proof, but the size of the proof is bigger than the size of the universe. Okay, fine. That's another gotcha. But if you look at all of mathematical progress to date, all the beautiful theorems we have, they're all reasonably sized proofs. So it would be a weird gotcha to be like, oh, no, trust me, a lot of the good proofs are like incredibly huge. Mathematicians don't think that it's going to be common for proofs to be ridiculously huge. Probably some of them are, but probably most proofs of interesting, deep, true facts will continue to be reasonably sized the way they have been throughout the history of human math. So what I'm saying is, when Penrose talks about computable AIs, how far can you get with a computable AI? I'm just giving you a taste of how powerful computability is. Computability can just plop out every true proof of every true statement in math as long as you can just do a search and run it for enough time. That's what computability gives you. So computability is hardly a barrier. I call it the highest ceiling imaginable. So Penrose is like scoffing at that and being like, no, you need uncomputability. And I'm like, why don't you just postulate something that's more reasonable? Like, hey, I bet the universe can search really fast. Or like, hey, I bet the universe is hyper-exponential in size, so that searching large spaces is trivial for the right physics. Why do you have to go all the way to it being literally uncomputable? It's crazy to me. In this next part, Penrose is going to talk about Gödel's incompleteness theorem, a really important mathematical result from 1931 that's closely related to results about the limits of computation, like Turing's result about the halting problem. Both of these results, Gödel's incompleteness theorem and proofs of uncomputability, they're both what I call ridiculously high ceilings. Like there's so many layers of ceilings below uncomputability and unprovability, which is what Gödel's incompleteness theorem deals with. Even if you allow things to be computable and provable, you still have like every possible input-output behavior that we could ever realistically fantasize about. Those are still contained within the ceiling of provability and computability. But let's listen to Penrose's take.
When I was a graduate student in Cambridge, I learned about Turing machines and the notion of computability, and I knew what computability meant, and I learned about Gödel's theorem. And Gödel's theorem I found stunning because it told you that there are things that the understanding transcends the use. Let me put that more clearly. What Gödel does is very clever. What he does is to produce a statement. Now, suppose you're trying to develop your mathematical methods of proof. What do you mean by proving a theorem in mathematics? How do you know it's really true? Well, you prove it. What does proof mean? Well, you see, does it mean, okay, you've got a set of rules, and if you follow these rules, that makes it a proof. Now, Gödel's theorem is extremely clever. You make a statement which asserts that it cannot be proved by these rules. It's just, the clever thing is to make it do it. It says, you give your rules, which you regard as the rules of proof, and you could put them on a computer. So that means they're computational rules. See, the Gödel theorem says, you construct a statement which says, you see what it means. The way you've constructed the sentence, you can see what it means. And what it means is, I am not provable by those rules. And it does that. It really says that. Then you see, okay, well, perhaps it is provable by the rules. Suppose it's false. Then that means it's provable by the rules. And if it's provable by the rules, you've understood the rules, you said, you looked at them all and said, yes, that's okay, that's okay, sure, if you follow those rules, it is true. So that means you believe, but the rules only give you truths. So therefore it is true that it's not provable by the rules. If it's false, you see, then it is provable by the rules, and therefore it's true. So it has to be true and not provable by the rules. I found that amazing.
Okay, that wasn't the clearest explanation by Penrose, but he's not wrong. Let me just try to summarize it in my own words. So you have a formal system. A formal system is basically like algebra, like in math class when you write a proof and you write a bunch of lines like x plus 3 equals 4y, x equals 4y minus 3, right? So the line under it is like a transformation because you follow rules to get from one line to the next line. So a formal system is kind of like you doing algebra in high school, except you don't get to use any creativity. All you can do is when you go from one line to the next, you have to follow syntactical transformation rules. So like a rule that says, okay, you can put a minus y in front of both sides, right? You can do the same symbolic transformation. So they're all purely mechanical rules. A formal system defines a bunch of different rules. It turns out that you can actually embed all of interesting mathematics that we humans like to do. You can embed it all inside a formal system. So it's called Zermelo-Fraenkel set theory, and it's basically like any object we've ever defined, you can ultimately break it down into sets where it's like, okay, well, it's actually a set of infinitely many other sets, and all the numbers are actually types of sets. So there's this formal system that just represents all of math as symbol manipulations, and all of the different things you're allowed to do are all compressed into these symbolic manipulations, and it's all really great. It's just really hard to search for proofs. As we know from human experience, there's like an exponential search space, and when you actually want to find a proof, good luck searching. But then when you do find a proof, you can write it down, just like algebra in high school, just a bunch of statements one after the other that all use legal transformations. And then the proof is computer checkable, or it's checkable even by the formal rules of math. Even if you don't have a computer, you can just define it as a correct proof within a formal system. And by the way, this branch of math, it's called meta-mathematics, because they're doing math on symbols that represent math itself. They're like, hey, look, this is math, and let's count how many transformations you can make before you get to the end of the proof. So they're doing math on objects that represent the act of doing math. So it's kind of cool. I was into that kind of stuff. I studied it in college. Okay, let's talk about Gödel's incompleteness theorem. The reason it's called incompleteness is because it points out that these kind of formal systems will never have a proof for every single true statement. They'll prove a lot of true statements, probably most of the true statements you care about they will prove, but there will always be some holes in the fabric, some statements that are true yet unprovable. And the existence of true unprovable statements makes the formal system incomplete, because complete would mean that if a statement is true, then it has a proof within that formal system. And Gödel's saying, no, there's no such thing as a formal system with consistent axioms, which is complete. There's no such thing. It's always going to be incomplete because I can construct some holes. I can construct malicious pathological statements that are going to be these unprovable holes. What was Gödel's trick? This is what Penrose explained. Gödel came up with a statement that says, I don't have a proof. And he put the formal system in a catch-22, because if the formal system had a proof for it, well, now it's proving something false, because the statement says, I don't have a proof, but the formal system has a proof for it. So the formal system's never going to do that. It's never going to get caught out in that kind of paradox. So Penrose is saying, okay, well, then there's no proof for it, but it's true. The claim that I have no proof, sure enough, there's no proof, so it's a true claim. So now you've got a true claim with no proof, so now the formal system is incomplete. So what I just said, that's Gödel's incompleteness theorem, and that's basically the proof. The most complicated part of the proof is probably something called quining, where if you want to write out a statement that says, I have no proof, that word I, you don't just get to say I when you write a formal statement. Like there's no word I in formal math. And so it doesn't actually say I. It says, hey, a statement with this big numerical index doesn't have a proof. And they set things up so that this big numerical index turns out to be the same numerical index that references the statement itself. So there's this method called quining where they get the statement to indirectly refer to itself. Like, hey, I'm just talking about a statement with this numerical index. Oh, that's me? I didn't know that, right? The statement is not directly aware of the concept of I. It's just talking about a numerical index, but they architect the statement so that it lines up so that it actually is talking about itself, even though it's just talking about a statement with an index. So that's one of the clever tricks in the implementation of Gödel's theorem. Personally, I think Turing's uncomputability theorem is simpler than Gödel's incompleteness theorem, and the two are very closely related. So I find it easier to think about uncomputability and the halting problem compared to thinking about incompleteness, just because incompleteness is pretty complicated with that whole Quining trick and formal systems. I find it easier to think about, okay, look, you have a computer. You think the computer can give you every input-output? Let me give you the uncomputability version of Gödel's proof. I'll give you the Turing side of Gödel's proof because it's basically a dual theorem. So Turing's uncomputability theorem, let me explain that to you, okay? Imagine that everything was computable. Then I could just define a function, and that function would have some Turing machine that would be able to correctly compute it. Okay, here's my function. The function's input is a Turing machine, and its output is some behavior that's different from that Turing machine. So now I've created a catch-22 because any Turing machine that claims to be able to compute any function, well, this is a function that's defined based on what Turing machines do, and it's purposely defined to do something different. It's kind of like if I claim to predict the future, you can mess with me by asking me to predict what you're going to do and then doing something different. Because of that paradox, I just proved to you that there's no such thing as a human oracle. There's no such thing as a human who can always predict the future, because if there were, some other human could walk up to them, ask them what they're going to do, and then do something different. That's the deep structure underlying the no predicting the future theorem and the halting problem uncomputability theorem and Gödel's incompleteness theorem. The deep connection here is that you can never have a system that claims too much insight. You can never have a formal system be like, oh, I can prove anything that's true. Really? How about I am unprovable? Anytime a system claims to have too much insight, you can put it in a catch-22 where you ask it to predict something that you then make wrong because you have too much expressive power. So that's the deep connection. So this is all very cool, but the problem with people like Penrose is that they think Gödel's theorem has practical implications about AI. In this next part, the interviewer basically asked Penrose, look, that's all well and good about formal systems that have their own predefined rules, but why can't the AI just make up its own rules and just reason about the implications of those rules and just do a total end run around Gödel's theorem, which is a question I agree with.
But still, I don't understand why AI cannot create its own rules.
Because it doesn't know that they're true. You see, that's the whole point about the Gödel theorem. The whole point, as far as I'm concerned, about the Gödel theorem is how do you transcend the rules? And that's what you do by understanding them. You understand them why they're true. It's not that you use the rules, but you understand why use of the rules only gives you truths. And that's how you can prove things which go beyond the rules, by knowing why they're true. Now, knowing why they're true, well, what does it mean? Well, it means you understand them. What does understand mean? You've got to be conscious of them. You see, the wording is clear. It means that you have to know what you're doing. You have to know why they're true, not that they're true. You can be told that they're true. You can learn at school that they're true. That's not the point. You have to know why they're true. Why they're true needs understanding them. And understanding them requires being conscious of them. Now you see, the point I was making is that consciousness enables you to transcend the rules. You see why they're true, and that goes you beyond it. You see, what the Gödel theorem does, it tells you how to use your understanding of why the rules are true to transcend the rules.
You can see Penrose is making a lot of hay out of Gödel's theorem. He's saying there's this formal system, there's a true statement in it which says I am not provable. I, Penrose, can see that that statement is true. The formal system can't see that that statement is true. It can't prove it. So I have a deeper understanding of truth compared to any formal system because of Gödel's theorem. I rise above using my human consciousness. And it's like, whoa, man, slow your roll. That is such an overblowing of Gödel's theorem. So let me give you two objections why I think Penrose is way off base, like not even close to making a coherent argument. Objection number one, the Gödel's theorem trick, it really is just a catch-22. It's not like the formal system could possibly do anything better. The Gödel statement is saying if you have these axioms, like the axioms of Zermelo-Fraenkel set theory, there's never going to be a finite line of proof that connects those axioms to me, to the Gödel statement. But let me ask you, what is the formal system supposed to do? We don't want it to prove that statement, because if it proves that statement, it proves something false. So it's doing the best it can. You're putting it in a catch-22. You're saying, hey, you better not prove me because that's going to be a paradox. And it's basically saying, okay, I won't prove you. If there was some way for the formal system to basically raise an alarm and be like, hey, this is a special statement. Not only am I not going to prove it, but I just want to point out that it's true and it's a paradox. If there was an escape hatch where the formal system could tell you that, maybe it would. But the problem is there is no escape hatch. The formal system just always has to either have a proof of something or have a proof of its negation or have neither. That's all it can do. In the case of the Gödel statement, presumably, unless there's something about set theory that we don't know, presumably it doesn't prove it true or false, because having a proof of it being true or false in both cases would be a contradiction. To make the second case more explicit, if a formal system contained a proof saying the Gödel sentence is false, and remember the Gödel sentence says I am not provable, then the formal system would be asserting that the Gödel statement actually is provable, which means the formal system would have to contain a proof of the Gödel sentence, and now the formal system would be proving the Gödel sentence both true and false. So this is what I'm saying. The only reasonable option for the formal system is to have no proof of G, the Gödel statement, and also no proof of not G. That's all we would want out of the formal system. We wouldn't want it to behave any differently. So Penrose is putting the formal system in a catch-22 and being like, look at this dummy. It doesn't even see the truth of the statement, right? Because it's not set up to be able to tell you that you're tricking it. This is the best that it can take the trick. It's like you're punching at somebody with no mouth and they're not screaming and you're like, look at this punching bag. Yeah, it's just taking your punches. What's it supposed to do? So I claim that Penrose and Gödel are coming up to the formal system and they're putting it into a catch-22, which isn't a fair fight, and then it's doing its best. What I want to do now is turn the tables, and I want to put Penrose in the same catch-22. So I walk up to Penrose. I say, hey, Penrose, check out the statement P. P says, Penrose can't prove me. All right, go ahead and prove P true or false. Now, if Penrose somehow finds a proof that P is true, he will have proven something false because P says Penrose can't prove me. If Penrose finds a proof that P is false, that means Penrose can prove P, so then he has to come up with a proof that P is true, but now he's come up with two contradictory proofs. So I've put Penrose in the same catch-22 that he put Zermelo-Fraenkel's set theory into. You can do that same catch-22 on a human too. So what would Penrose respond when I ask him to prove the statement P, Penrose can't prove me? What would Penrose respond? The only dignified response is to be like, nope, I'm not going to give you a proof of P or its negation. I'm not going to be a fool. And that's the same response that Zermelo-Fraenkel set theory gave. So look, Penrose, I just pulled the same trick on you. I put you in a catch-22. Does that mean I'm more insightful than you because I pulled that trick on you? Am I more conscious than you because I put you in this catch-22? And no matter what you say, you look like an idiot and I look smart? It's such a low blow to ask a set theory or to ask a person to grapple with a statement like P or G. These are pathological statements where you're specifically just trying to catch out the system in a catch-22. You can do it on humans. You can do it on formal systems. Okay, so that's my second pushback to Penrose thinking Gödel's theorem is really significant. Here's my third and final argument as to why Penrose is making way too much out of Gödel's theorem. Let's go back to the Gödel statement G inside of formal Zermelo-Fraenkel set theory. We outsiders know that ZF is never going to prove G, because if ZF did prove G, then G would be this assertion that no proof of G exists in ZF, and yet a proof of G would exist in ZF, so then G would be false and yet proven by ZF, which breaks the very integrity of ZF. Like, we all came in with the assumption that Zermelo-Fraenkel set theory is just the laws of math. It's just how we do math. And it's a self-consistent set of axioms. It's not like they contradict one another. Well, that is indeed the assumption that we came in with, that the ZF axioms are a coherent way to do math and they don't contradict each other. That is how we as humans argued to ourselves that G doesn't have a proof within ZF. That's why we're so smug and we can see that G is totally true and yet doesn't have a proof. But here's the thing. That whole argument that we just made, you can actually translate that argument, the very argument of Gödel's incompleteness theorem. You can actually translate that argument into the language of ZF set theory. So ZF set theory can actually follow the argument of why G is not going to have a proof within ZF set theory. It just requires one extra assumption, which is that ZF is consistent. The axioms of ZF don't contradict themselves. If you explicitly tell ZF, hey, did you know that UZF are consistent? You never contradict yourself. Now, do you think that you prove G? If you ask that to the formal system would say, oh no, then I don't prove G, because it would follow the same logic that we just followed when we proved Gödel's incompleteness theorem. So it would see exactly what we see as long as it gets to assume that it's consistent. This means the only difference between ZF itself and a human looking into ZF, the only difference is that humans just pre-assume that ZF is consistent, whereas ZF isn't allowed to pre-assume that because the act of pre-assuming that actually lets it prove G, which creates a contradiction. So ZF isn't allowed to assume that ZF is consistent. It has to be humble about whether its own axioms are consistent. It's not allowed to reason based on the fact that they are. Whereas humans come in and they're like, you know what? I just think ZF is consistent. I just intuitively think it's totally consistent and it's never going to prove a contradiction. Now you might ask, well, isn't that a really good intuition? Why doesn't ZF have good intuition? And there's another aspect to this, which is that like the consistency of ZF, or like the whole notion of a contradiction existing. ZF can assert, well, look, a contradiction does exist within myself, but the contradiction is like really high up in the numbers. It's basically infinitely high in the indexes of statements. Like, yeah, a contradiction exists. Can I actually find it for you? Not really. I can just tell you it's really, really big. It's like bigger than any number you can name, but I'm telling you it's up there. It's up there in the numbers. And it kind of plays with the definition of numbers and the definition of finiteness. And it'll be like, yeah, a contradiction exists somewhere, man. So it's like this abstract notion of existence and finiteness. Like, this is what happens when you try to push on these formal systems, when you get into mathematics. They start telling you about the numbers that exist, and they really don't feel like numbers, but they insist, trust me, man, this is how numbers work, okay? They just get really, really big. I can't name a specific number, but it exists out there in number space, and my own contradiction exists somewhere in this like transfinite region. That's basically what formal systems start to tell you when you start pushing them really hard to try to find a contradiction, and you can't actually pin them down. So like there is such a thing as ZF plus the claim that ZF is inconsistent. So it's actually not as easy as it seems to be like, what? Of course ZF is consistent, because the claim that it's inconsistent is kind of defensible in this like really weird way. So anyway, this is the truth about metamathematics. This is the actual flavor of opening up the can of paradoxes, putting in a catch-22, and watching it try to squirm out of the catch-22, which it does surprisingly well, right? Like it invents this whole concept of like transfinite numbers that can substitute for numbers. Like it's very good at squirming. It's as good as you could ever imagine. It's better than Penrose himself. When I asked him to prove P, he would probably give up more easily than this formal system, where the formal system says like, oh, I can prove it. The proof just has a really, really, really high number. Like that's one of the moves that it does. So anyway, I just told you the real nature of Gödel's theorem and what to really make of it, which is nothing. There's no alternative to formal systems not proving G. You put it in a catch-22. There's no takeaway from this, besides the fact that expressive power lets you get recursive and weird and funky. Yeah, things get funky because there's no other way that they can. You trapped it. You made it so that if it doesn't get funky, then it has to get paradoxical. It's not going to get paradoxical, so it got funky. You caused this. This isn't a weakness in the formal system. This is just you trying to push it into a corner, trying to trap it, and this is what happens. But it has nothing to do with the limitations of the system. The system is incredibly powerful. The computers within the system are incredibly powerful. You don't need consciousness. I'm not more conscious than Penrose because Penrose couldn't answer P. So he's just completely, wildly misinterpreting Gödel's theorem, and everything he says after this point is just based on something extremely flimsy and wrong.
You think that AI is the simple tool or simple thing that we can use in the single case?
No, I don't say single. It's obviously infinite. No, clearly, that's not the point. The point is it doesn't know what it's doing. That's still true with AI. You talk to an AI thing, it doesn't know what it's doing.
If I understand correctly, which I think I do, Penrose is saying, AI doesn't know what it's doing in the same sense that formal set theory doesn't know the truth of the Gödel statement. It doesn't have insight. We know that we have insight because we can see the truth of G, and formal systems don't have insight because they can't see the truth of G. And so AI is never going to have insight about itself because it's just one of those formal systems, and formal systems don't have insight about it themselves, which again is just wildly misinterpreting the Gödel sentence. He's making so much more out of the Gödel sentence. Like in real life, can an AI have insight? Can it know what it's talking about? Of course, because it has a very detailed model. You know, it has a high-dimensional vector space where a word is embedded and has like super detailed connections to other words. Like that is literally what it means to know meaning. Meaning is like an isomorphism between embedding a concept in this high-dimensional space, and then that has similar relationships to relationships in the real world. If that is your configuration, then you understand the meaning of something. Like we actually know what meaning means, thanks to the last decade of AI research. And Gödel's theorem has nothing to say about that. Zermelo-Fraenkel set theory doesn't know what snow means any better than a human or a modern AI. The whole concept of meaning and knowing what you're talking about in the sense of concepts and relationships between concepts has nothing to do with formal set theory or Gödel's theorem. And it just seems like Penrose is just not even talking in this universe. I don't know why. Okay, now it's time to bring in friend of the show, Dr. Scott Aaronson. You may remember a few weeks ago, I did an episode about OpenAI's safety research team and what a disaster it is, as proven by Scott Aaronson's account of his time there. Well, Scott watched the episode a few days later, and he posted the nicest review I've ever gotten, where he highly recommends that people go watch the episode, including the part where I quote, "Tear him a new asshole." So listen to Scott, give that episode a look, and then come back and watch this part. Because for this part, we're going to go back 20 years, back before Scott published his amazing theoretical computer science results, back when he was known by kids like me surfing the early internet as a smart guy with a personal homepage and a blog and a great sense of humor. This is a joke page that he put up like 20 years ago. It's called the Gödel CAPTCHA. And the point of the page is specifically to make fun of Roger Penrose and how he thinks about the Gödel incompleteness theorem being this huge barrier between humans and AI. So Scott writes, a CAPTCHA, which stands for Completely Automated Public Turing Test to Tell Computers and Humans Apart, is a test that a computer program can generate and grade and that humans can pass, but that current computer programs cannot pass. Such tests are used by Yahoo and other internet portals to deter robots from abusing their services, for instance by registering for thousands of free email accounts and then sending spam from them. The trouble with the current tests is that it's difficult to know how secure they are. So the obvious question arises, does there exist a CAPTCHA that is unconditionally secure against any machine, present or future? I am pleased to report an affirmative answer. It's inspired by the books of Roger Penrose, The Emperor's New Mind and Shadows of the Mind. You can try out my CAPTCHA below. And here's Scott's sample test. Given a formal system F that contains piano arithmetic, consider the following Gödel sentence which asserts its own unprovability in F. And then there's a big box that says G of F. And this is exactly the G that we were talking about before, the sentence that says, I am not provable, the sentence that Roger Penrose thinks only humans can see the truth of. So Scott asks, is G of F necessarily true assuming the axioms of F? Yes or no? So because I'm a human, I have the insight about the consistency of F and the fact that G is true even though F is never going to prove G. F is the formal system. Remember we talked about Zermelo-Fraenkel set theory as an example of a formal system. Okay, so I'm going to click yes because I have human insight. So I'm going to pass this CAPTCHA. And now the page says, for humans, congratulations, your answer is correct. For automata. Although your answer happens to be correct in this instance, you could not have arrived at it via a knowably sound procedure, as you do not possess the requisite microtubules. Thus, we cannot currently offer you an email account. Please try again. Do you get the joke here? Scott's basically trying to make the point of, look, Penrose, you think humans have this special access to truth, but in practice, whenever it comes time to apply that insight, isn't it just a matter of clicking a button that an AI can also understand and click? Can't an AI just look at this test and be like, oh, you want to know whether G is true in Zermelo-Fraenkel set theory? Yeah, sure, because if it were provable, that would create a contradiction. Like, in reality, an actual AI in practice can follow our logic. And you could be like, wait a minute, but how does the AI know that ZF is consistent? It doesn't matter. It can just assume it's consistent the same as we can. It can just get the job done. These aren't actual practical barriers between humans and AIs, right? The exact same point that I was making. More generally, Penrose just doesn't see the world from a functional lens. He's just not interested in testing what AIs actually can and can't do and comparing it to what humans can and can't do. He doesn't want to go dive into that. He just wants to say that humans and AIs are fundamentally separate because humans have more insight, and basically just leave it at that. He's not really curious to explore the functional differences. And Scott Aaronson is just pointing out, look, if you try to design a CAPTCHA, you're not really going to have any leverage. You're not having any head start, any advantage designing a CAPTCHA because you believe what Penrose believes. If you believe that human intelligence is uncomputable and based on microtubules, how does that let you design a CAPTCHA? It doesn't. You're still stuck. You're still on square one using the same CAPTCHA techniques that anybody else would use who doesn't believe human intelligence uses uncomputable physics. All right, so that's the Gödel CAPTCHA by friend of the show, Scott Aaronson. Go to scottaaronson.com for more of these gems, or go to the Doom Debates archives and watch my episode about Scott Aaronson because he recommends it. Moving on.
You see, people have confused the story. They've lost it in the power of computing. The thing is that computers have got so powerful that they've lost the thread of what they're doing. I think Turing wasn't too far off. You see, he was a little bit confused person in a way, because it was not clear what he believed. But he did call this thing the Turing test. How do you decide whether an entity is conscious or not? Well, you have a conversation with it. You talk to it.
Maybe AI is a new sphere of human existence.
No, it's missing something.
Penrose started talking about the Turing test and the interviewer kind of cut him off. So let me explain Penrose's position on the Turing test. Penrose doesn't like the Turing test because the Turing test is just about input-output behavior. And Penrose thinks that even if an AI can pass the Turing test, that just means that it's mimicking human behavior, but it doesn't have human intelligence or human consciousness because it lacks true understanding and it lacks the hardware, the quantum microtubules. So Penrose just isn't impressed with the form of the Turing test, the idea that just an input-output test could be enough to reveal that an AI is truly intelligent. Whereas from my perspective, I think this is Turing's perspective. It's more like, hey, if it's answering all your questions really intelligently, then it's intelligent. Like, that's a really good definition for the word intelligence. I don't know why you would define the word differently. And these tests aren't easy to fake. So the idea that it would be just mimicking human intelligence, okay, I mean, mimicking human intelligence, nobody's ever done it before. We've worked on it for almost a century now, mimicking human intelligence, and we haven't fully cracked that, have we? Because by the time that you mimic it perfectly, it means you can do everything that it can do. So hey, how about mimic building the most powerful rocket company that's ever been built? Can you mimic that? Okay, well now you have access to the best rockets that have ever been built. Can you mimic a brilliant scientist building nanotechnology? Okay, well now you have nanotechnology. So I don't even know why he would bust out the concept of mimicking instead of just admitting yep, the Turing test is a pretty good intelligence test. I don't get it. Penrose is also a believer in the wisdom of Searle's Chinese room argument. So I can go over that real quick. It's this idea that if you're inside of a room and you have a rule book with all the rules of how to talk Chinese, and somebody slips a paper under the door with a question for you written in Chinese, and you don't know Chinese, you just have this rule book, and you just start flipping the pages in the rule book, being like, okay, the first character is this, so I go to this page, and then the second character says to look it up in this table if these first two characters are present, and then oh, the third character actually brings me back to this page. So the rule book is kind of an algorithm. So you just start flipping around, going back and forth, maintaining a notepad because the rule book is telling you to have a scratch pad where you do operations on the scratch pad. So you're doing all of these things. And at the end of the process, you output a slip of paper that has a response written in Chinese, and you still have no idea how to speak Chinese. You're just a rule monkey who followed the rules in the rule book. And John Searle, who came up with the experiment, his point is look, it's not enough to just look what goes into the door and what comes out of the door. Clearly, you can have a system that mimics intelligence without being intelligent, or you can have a system that mimics understanding Chinese without actually understanding Chinese. Because look at this rule monkey, he clearly doesn't understand Chinese. And the book doesn't really understand Chinese. It's just a book of Chinese rules. It's different from understanding Chinese. So nothing really understands Chinese. You just have to be a human brain if you want to understand Chinese. Now, the first time you hear that argument, it's kind of compelling. It's like, oh my God, it's just a person following rules in a rule book. Here's the catch. The rule book is actually, it's not even a book. Like if it were actually a book that had lookup tables, it would be larger than the size of the universe because there's too many different cases of what you have to respond in which case. So if it's actually an algorithm for speaking Chinese, what does it look like? It looks like the inside of an LLM. Like, oh, okay, it has billions of numeric weights, and the weights get updated, and different parts represent different high-level concepts, and the concepts interact with each other, and reasoning steps happen about what's actually being discussed. If you're a human who's manually using a scratch pad to implement every single step in an LLM, you're kind of like an NVIDIA H100 GPU. Yeah, you're going to be there for a very, very long time manually using a scratch pad to flip every bit that gets flipped in the operation of a NVIDIA GPU. We're talking many billions of operations. We're talking a rule book that is actually, many billions of weights worth of rules and many forward iterations through this large structure, like a neural network structure. And yeah, you're talking many, many individual steps. By the time you're seeing all of this happening, if this is all happening in, let's say, under a minute, then this is happening at like the speed of light. Like the guy following the rules, he's going at light speed. And if you look at all the signals flying around during that operation, if you look at how many little Post-it notes have to move around, you're now looking at something which is actually as complex as the inside of one of these NVIDIA GPUs, or as complex as the inside of a human brain. You're looking at major data processing happening. Like the metaphor of a rule book doesn't capture it. And so, yes, these giant systems with a lot of data flying around that are representing concepts in high dimensional space connected to other concepts, yes, these kinds of systems do understand things. John Searle just made up a visual metaphor which is actively misleading. It looks nothing like a book. It looks like an information processing system, which is what a brain is, which is also what silicon is. Like there's actually a pretty clear analogy between the information processing, how much of it there is, how fast it has to go, how complex it is. It's all analogous. So yes, a chip with a neural network is a lot like a physical neural network. They even call it a neural network. Searle's Chinese room is just pointing out that, silicon and brains are like different physical things. I mean, to me, this is like an incredibly shallow thought experiment once you realize that the original visual metaphor is just intuitively misleading. And the actual visual metaphor is incredibly similar between human and machine. So I bring all of this up because Penrose thinks Searle's Chinese room is making a profound statement about AI sometimes not truly understanding things the way humans do, whereas I think Searle's Chinese room is just like a totally misleading, unproductive thought experiment.
Sure, computers have got so powerful now that they can do things way beyond what humans do in computing, sure. And you can take a massive data and you can analyze that data and you can see what the data says and does this thing in accordance with previous things in the data or is it not? And AI, that's all it does. It doesn't understand what it's doing. And understanding is different from computing.
Because inside a black box, there is just only statistic. There's a simple statistic machine.
Well, if it's a machine, it's not conscious. No, I think people have lost the plot, yes.
Yes, you can just take a massive data and analyze it in accordance with other data, but you don't really understand what you're doing. It's all about understanding what you're doing. Because when you understand what you're doing, that lets you take other data as input and then process that new data differently because you mix it with understanding. Because ultimately, we all know it's still data processing. There's still an input and an output. And the relationship between the input and output can still be incredibly powerful. But Penrose must be claiming that when you mix in understanding into the input, then the relationship between the input and output can get super powered. You can have outputs that you could never have before if you only were just crunching data without understanding it. I just want to go back to Zermelo-Fraenkel set theory for a second, because if you give it the condition that it is consistent, if you add consistency of ZF as one of the axioms to the new formal system, it can see the truth of Gödel's statement. It can follow the human's logic step by step. So given that even these formal systems that it claims are so lacking in understanding, They're just one little hint away from seeing exactly what he sees. And yet he's so dismissive of like the fundamental nature of these systems. I don't get it. Like the guy is so smart and so old. He's had so many years to think this through, and he's still so stubborn on this idea that they can't have true understanding.
My train of thought was, we've got to find something in physics. See, I believe, I'm a physicalist, in that I believe whatever is going on in our heads, whatever creates consciousness, is part of the physical world. What I'm claiming from the Gödel argument, you see, this is the plot which I think has got lost. What I claim is saying that the physics that is involved in conscious thinking has to be non-computable physics.
He's basically the most magical possible physicalist because he admits, yeah, every phenomenon is a physical phenomenon. There's not multiple types of phenomena because whatever type of phenomena there is, you can just call it physical and you can just try to do science on it. Why not? Like, what would it mean to have a different type of phenomena? So at least he's clear-headed about that. It's just the type of physical phenomena that he thinks exists are totally unjustified. He thinks physics is uncomputable. He thinks there's no computable explanation for the input-output of the human brain. Like the human brain has outputted things that are so powerful and magical that there's just no way to relate those inputs to those outputs with a computational model of any kind, even an ideal kind in all of algorithm space. If you had a perfect search through all of algorithm space, nope, you're not going to find the human algorithm because the human algorithm transcends computability theory, and the laws of physics transcend computability theory. Oh, the evolution of the universe from one time step to the next? Nope, there's never going to be a simple or even a computable description for that because the laws of physics are uncomputable, according to Penrose. There's a quantum collapse stage that there's just no computable way to explain what's happening, and that's what gives humans our intelligence and our consciousness. This is the world according to Penrose. I'm just fleshing it out. But it's funny that he's saying, look, I'm just a physicalist, okay? I'm not positing any magic. Nope, no magic, just uncomputable physics. I will give him credit for not trying to go so woo-woo and be like, physics isn't all there is, man. There's something beyond physics, because that statement is actually just epistemologically meaningless. So he's not unnecessarily throwing away good epistemology. He deserves some credit for that. It's just then he goes on to be like, yeah, and physics is full of these mysterious rules that, in my opinion, really have no reason whatsoever to be hypothesized, but he loves hypothesizing them, right? That's his claim to fame, is these microtubules with these quantum effects. That is his whole thing, and a lot of things are connected to that thing for him.
Now, the physics we know, there's a little bit of a glitch here because it's not completely clear. But as far as we can see, the physics we know is computable.
You think?
You see, what about general relativity, where we have wonderful machines which compute what black holes do when they spiral around each other and produce gravitational wave signals? And you can say, yeah, that is a black hole collision because this has this very clear feature. And yeah, you can do all that. That is fine. But that's not what I'm talking about. What I'm talking about is the physics has to be a physics which is, in principle, non-computable. So AI can blast this, go ahead as much as it likes. It's not going to be able to get this.
You guys know James Randi, the amazing Randi, this famous stage magician and skeptic who died a few years ago. He used to go around debunking psychics and mystics who could talk to the dead and all these people who claim to have magical powers. He would go around and he would do the same thing using trickery. Like, oh, Uri Geller can bend the spoon with his mind. Look, I can bend this spoon using simple trickery, but it looks exactly the same. It's the exact same effect. He claims to be doing it using magical spirits. I'm doing it using cheap trickery. And what he would say, the quote that James Randi would say about all of these mystics, he'd be like, look, they're doing it the hard way. If they're tapping into the realm of the dead so that they can get the spoon bending effect, they could just be doing this. Why are they doing it the hard way? Because this could be done by cheap trickery. I'm not saying this particular mystic is using cheap trickery. I'm just saying they could be doing it this way. So if they're doing it any other way, they're doing it the hard way. And that's what I say to people like Penrose. You think we need uncomputable physics just so that I can sit down and write an essay that has reasoning in it? You think uncomputable physics is the source of me doing that? Or if I go run a company and I'm trying to make financial decisions of what to buy, where to make the company's investments, You think I need to tap into uncomputable physics, into mystical quantum collapse, just so that I can make good decisions to run my company? Penrose, you're doing it the hard way. There's easier ways to get this stuff done. You can just use neurons that propagate weights according to computable laws. You can get really far going this way. In fact, you yourself can't even put exact limits on how far we can go. You just dismiss the whole thing by saying, oh, passing the Turing test, that's just mimicking behavior. You could mimic arbitrarily complex behaviors without uncomputable physics. So all of these things that Penrose is postulating, like, oh yeah, these uncomputable physics totally exist and they're so powerful. They might be so powerful, but they're doing things the hard way if the human brain is using uncomputable physics, because we have silicon, and the silicon is now able to write an essay and pass really hard tests of various types faster and better than humans can. So the fact that we're here using uncomputable physics, this ultra powerful special thing, and AIs are here just whipping it out, doing it faster and better without using uncomputable physics, we're very much in the position of the James Randi mystic, where we're achieving the same effect, but we're doing it the hard way. And of course, I don't think we are. I think we're also doing it the easy way, and I think we're doing a sloppy version of the easy way, and I think we're building computers to do a much better, more robust, more powerful version of the easy way, and I think the easy way is the only way. I think just using computable physics is the only way, but it's a really good way.
AI, as we now know it, is computer-driven.
Superhumans, AI will never exist?
Well, the trouble is that AI is a bad term. It means artificial intelligence. Now, intelligence, in my view, is conscious. That's what intelligence is about.
Okay, so how I can call it?
Artificial cleverness. How about that? AC. You can see the difference to some extent when you do mathematical. You have mathematics students. Some of them understand what they're doing. Some are just clever. They can repeat what they've learned. They know how to do it very cleverly. They can calculate very well, but they don't necessarily understand what they're doing. The physics we don't know involves non-computability. So that's my claim. So I made this claim in The Emperor's New Mind. And I've made it a little bit more forcefully in Shadows of the Mind.
I admit I haven't read Penrose's books, but I'm confused about where he thinks he can draw the line when there's a system that doesn't use uncomputable physics, when there's a merely computable system. He gives the example of his own math students where sometimes they don't really understand what they're doing. So maybe that means that they haven't turned on, they haven't tapped into their uncomputable microtubules. They're only using the purely computable algorithmic parts of their brain, so they don't really understand what they're doing. And then the students that turn on this uncomputable turbo boost, maybe they're proving deeper theorems, they're doing math better. But we've already established that the actual practice of doing math, if you could do a computable search through all of math, the computability would still get you there. It would still get you to every proof as long as you had enough time. So maybe what Penrose thinks is, yes, math is computable, but you can search it faster if you can do an uncomputable search. Or you can search it faster if you use this particular algorithm, which happens to be uncomputable, but that's not the interesting part of it. The interesting part is not that it's mapping inputs outputs in an uncomputable way. The interesting part is that it's actually very efficient. So when you talk about this magic algorithm that the human brain is supposedly doing, I wouldn't even refer to it as the uncomputable algorithm. I would just refer to it as the really fast algorithm. And when you talk about uncomputable physics making these kinds of algorithms possible, the algorithms that potentially violate the complexity theory version of the Church-Turing thesis, which is saying like, hey, if you can do something quickly in the physical universe, it must be in this complexity class P or BQP if you're using a quantum computer. Penrose basically wants to violate this complexity theory version of the Church-Turing thesis because when you have an algorithm that's finding really good mathematical proofs in a reasonable amount of time, that algorithm is solving a problem that we know is in the class NP. But maybe it's not doing it by executing any polynomial time algorithm. Maybe it's doing it by somehow skipping ahead using uncomputable physics, and not only uncomputable physics, but like non-algorithmic physics. Like it's running an algorithm which is running in polynomial time, but not by using a polynomial number of steps that we can model as steps. It's just somehow jumping to the answer. It's polynomial time because it's not taking steps. It's just physically, using special physics to get there, and you just can't explain. There's no mathematical model of how those physics works. So I'm just describing Penrose's model of the world of how these insightful mathematicians that he works with might be arriving at their proof by doing something better than just running a computable algorithm. That's like my best version of what Penrose must be thinking. But again, back to the question of where does Penrose draw the line in terms of powers that you can have when you have uncomputable physics versus powers that you can only have when you're just a computable algorithm. Remember when he talked about the Turing test, he still said it wasn't a good test because an algorithm, a computable algorithm, could still potentially mimic humans really, really well. So that implied that the line of doing things the easy way is potentially very, very high. Like that implied that he thinks, oh, you could have a computable algorithm that could mimic humans to the degree of passing the Turing test, meaning they could basically answer any question that a human could ask of another human. So I really have no idea where the line is in his mind. Like, I don't know if he expects that a perfectly computable neural network algorithm can still come over without being conscious and still take over the world. I don't know if he thinks that's possible. Like, the interviewer is just not asking him the obvious, interesting question here.
You see, if you're talking about AI, that means, unfortunately, it's a bad term because it says artificial intelligence. Which to me, when people use that term, they mean things that can be done by computers. I haven't studied these things, so I'm probably out of date, but as far as I can see, what it is you look at masses of data and then you sort of look for patterns or you try to analyze it in that kind of way. But it's all computational. You're using computers. By its very nature, it's computational. The word means computational, means by a computer. Now, a computer is a very specific kind of mathematical structure. It means computational mathematics. If you study the mathematics as an abstract subject, you rapidly learn that there are things way, way beyond computability. It's a very limited part of mathematics. Some of the mathematics that's involved is not computable. You can't get at it by an algorithm.
This is such a misleading framing of math. He's like, yeah, if you study math, pretty quickly you learn that there's this uncomputable realm, and there's actually tons of stuff in the uncomputable realm. Yeah, technically, in a certain sense, there's actually more uncomputable mathematical objects than there are computable ones. There's a sense in which you can have infinite cardinalities of uncomputable things, which are larger than the cardinality of computable things. There's definitely only countably infinitely many computable things, if you know what that term means. But this is completely misleading because when you go study uncomputability, what you quickly find is that all the good stuff is computable. And uncomputability, it's just this bizarre niche that some weirdos make their career out of studying the details of, but it has zero relevance because it's such a high ceiling for something to be computable. So when you restrict your life to just computable things, that's where all the good stuff is. All the good math, like 99% of all math, just takes place within studying computable things. It's rare to run into something and be like, oh man, it's uncomputable. This is hurting me so much. This is uncomputable. That never happens in practice. Take the example of finding a proof. In the general case, an algorithm which outputs a correct proof of any true proposition is uncomputable. That's what Gödel proved, right? Okay, but practically speaking, if I pose to you the problem, find any proof of 1 billion characters or less of whether this proposition is true or false, that is absolutely computable, right? It's just 2 to the power of 1 billion search space. And in principle, you can just crunch through every single element of the search space and you can find the proof. So the only way in which proof finding is uncomputable is because of this prospect that some proofs exist, but they're just ridiculously long and unwieldy, which again, in practice, proofs are never really like that. It's pretty unheard of to find a really, really long, unwieldy proof. Either the proof has a somewhat reasonable length, or there is no proof, or the opposite is true, or the proposition is independent of the formal system. But if there is a proof, in our experience, the proof doesn't have to be more than 1 billion characters. Any proof that humans have ever dealt with or published has fit within 1 billion characters. And the problem of deep insight, using your ultimate deep insight to find a proof that's 1 billion characters or less, guess what? That's well below the ceiling of computable. Finding a freaking proof, the deepest problem there is, if you limit it to 1 billion characters, is fully computable. So what is Penrose off about? Why is he representing uncomputable as being this, large, fascinating domain that you quickly learn about? It's not. It's a freaking ghetto. the land of uncomputable things, nobody ever talks about it.
The physics of the world could easily be non-computable. And my view is that, yes, it is non-computable. And that somehow nature has been clever enough to produce beings which can tap into the non-computable aspect of the physics. And they managed to do this using natural selection. I have no idea how far down the animal kingdom goes. Humans are certainly conscious. I believe anybody who owns a dog was absolutely convinced that dogs are conscious. I believe it. Cats, probably. Elephants, certainly. Way down, way down, probably. Octopuses, I'm sure. But I don't know. Is a bacterium conscious? I have no idea. Is a frog conscious? Probably, yes. Is an amoeba conscious? I have no idea. I'm just speculating. I have no real reason for leaving these things.
I can give you one reason. Animals don't do things the hard way. So if frogs are conscious, just so that they can jump around and go toward positive stimuli and avoid negative stimuli, you don't need to tap into uncomputable consciousness just to do that. Jesus, I thought the line was going to be like, oh, human mathematicians use their uncomputable consciousness to find a deep insight, to let them find a proof faster than naive search would let them find them. No. He thinks that a frog taps into an uncomputable consciousness just so that it can croak. Like, what are we talking about here? Why is nature doing things the hard way? Why is it not just using muscles, using neurons to respond to stimuli? Like, what's the problem here that consciousness is coming in to solve? Why is it this unnecessary appendage, consciousness? Actually, I do think consciousness emerges from certain functional structures, like structures in your brain that make pain feel bad. Like those probably actually do help animals survive. So there's a sense in which consciousness isn't doing something the hard way. Like there's a sense in which, nope, this is actually an efficient structure to get the frog to do certain simple behaviors. Fine. That may be true about consciousness, but now we're not talking about uncomputable intelligence. We're not talking about the computational difficulty of jumping away from a hot frying pan. Now we're just talking about like, okay, this is an efficient system that can get the job done using fewer moving parts, but that's very different from invoking consciousness to explain why a PhD student can find a proof better than any algorithm even could in principle, right? That's a very different discussion.
But I think consciousness is something different. It's not computational. And the thing is that it's just people are so hypnotized, I shouldn't use a rude word like that really, by the fact that computers have got so powerful that, yeah, there's the answer. The computers are so powerful, we found the answer. It's just computers. I'm saying, no, it's not. The answer is something much more deeper than that. It's not more complicated than that, it's deeper than that. It involves a kind of physics which we don't probably know yet.
It depends on what the question is. If the question is, what does it mean to truly understand the meaning of words and concepts, and to apply them to write a novel essay about a novel prompt, I think I actually do have some recent insight into that particular question, using modern neural net AIs that aren't conscious, presumably. I think I do have new insight into that question, don't I, Roger Penrose? Because this is a new capability that we never understood how to do, and now we found a way to do it. Maybe humans do it by tapping into uncomputable physics, but it sure is interesting that there's a neural network architecture, kind of similar to our brain's architecture, that is achieving this thing that used to be a mystery, and now it turns out to have a pretty simple explanation. Like these high-dimensional vector spaces actually have a very simple architecture, so encoding meanings, embedding meanings of words, turns out to be very simple and elegant just to involve a lot of data. Oh, that's interesting. So when Roger Penrose frames this as like, oh, people think they understand something, but they really understand nothing, like AI, they're barking up the wrong tree. Really, it sure seems like we just cracked what it means to know something in terms of like the meaning of a concept. Sure seems like we just cracked this age-old philosophical dilemma, didn't we? You really think that part is uncomputable when there's such an elegant, computable way to do it? Why would it be uncomputable?
It's deeper because it's based on the quantum world.
It's beyond the quantum world. You see, the quantum world is still computable. What's not computable, as far as we know, there's a basic unknown in quantum world. The quantum theory is fundamentally incomplete, as I call it even wrong in a certain sense, because it believes that quantum superpositions persist at all levels.
An important distinction with Penrose is he's not asserting that the brain is a quantum computer. He thinks something about quantum physics is uncomputable. So quantum computers are totally computable. There's nothing uncomputable about David Deutsch's quantum computers, but Penrose is on his own level where he's saying, look, something we don't understand about quantum collapse, it collapses in such a way that it seems totally random to any classical algorithm because it's an uncomputable algorithm, and these kind of uncomputable algorithms give you power. They let you skip to the truth of a mathematical theorem, right? It's skip to proving. I mean, they don't tell you what the proof is, but they somehow guide you toward finding a proof and outputting it in a fast amount of time so that you can beat classical algorithms by doing this uncomputable mapping from inputs to outputs. Like, that is the Penrose cinematic universe where it uses quantum effects, but it's not a quantum computer, and it totally helps humans be insightful, and also frogs do it. It's weird stuff.
Maybe when we ever create the universal quantum computer, we can create a synthetic consciousness.
Maybe. Yeah. No, I've nothing against it apart from the fact I don't like it. No, I have nothing theoretically against that.
So I give Penrose some credit for biting the bullet of what he's saying. So he's saying, hey, consciousness is purely physical. Yeah, it's using weird uncomputable physics, but it's purely physical. So when the interviewer asks, okay, so eventually we're going to build AI that uses the same physics, and he's basically saying like, yeah, I think that will eventually happen, or that can eventually happen. It's just not happening now because we've so embraced this paradigm of computability. Like, everything we build is computable, and it's based on the subset of physics, which we know is computable. So we're totally barking on the wrong tree to get uncomputable conscious intelligence. But maybe someday engineers will go figure out what's going on with these quantum microtubules, and suddenly we'll have this other track of AIs which are intelligent and conscious and powerful the way humans and frogs are. I mean, at least he's admitting that it's not so magical that it'll always be uniquely human. He's just saying it's a totally different engineering track. So entrepreneurs out there, if anybody ever wants to build uncomputable microtubule computers that Penrose will say are true artificial intelligence, seems like there's an open opportunity. I mean, I don't really think there is, but you'd think by now some enterprising entrepreneur would have raised tens of millions of dollars from venture capitalists who don't know any better. I think I just gave Jeff Bezos his next idea.
My question too is about this self-driving car. They are processing the hundreds of data. Maybe there is the consciousness.
I don't think they're conscious in any sense. But they could drive better than humans, that's possible. I don't know what the comparison is now. They certainly make stupid accidents from time to time, but so do humans. So it may be that they become more reliable than humans, and that may not be too far off for all I know. I have no complaint about that. I don't think that's any indication that they have consciousness. After all, we have devices which already turn off the lights at certain times, and maybe they know better when it's getting dark and so on, or how to economize on the use of electricity and things like that.
So again, the interesting question for Penrose is, what do you actually need consciousness or uncomputable physics to do? Because if AI can do the self-driving cars, if it can fully pass the Turing test, if it can run companies, if it can do projects better than humans can, if it can replace every single human function, and humans are still over in the corner with our uncomputable physics, don't you think at some point you should be asking the interesting question of what's the most powerful thing you can do? Like, what's going to make you 10 times better at thinking than humans, even if it's not uncomputable consciousness? Don't you think somebody should be asking that question? Aren't you interested in that question, Penrose? What if we forget about implementation details for 1 second and just ask, look, this work that intelligence does, this kind of search work, this mapping from inputs to outputs, this finding mathematical proofs efficiently, however it's done, the nature of the work being done, regardless of its implementation, regardless of its physics, what if that kind of work were somehow sped up? How much could it in principle be sped up? Could we, in principle, build AI that either uses classical computation or taps into the uncomputable microtubules, one way or the other, just does 10 or 100 times better than humans? Is that possible, and what are the implications? And are there signposts that computable AI might be on that track to do something that, yeah, you could also do it with uncomputable physics, but it looks like the computable track is blowing past any goalposts that we set for it, and it may also be heading into that territory of being 10 or 100 times better at thinking than humanity. Shouldn't we be on the lookout for that? Regardless of whether Penrose is right, isn't that a whole interesting field of study that should also be part of the discussion? Shouldn't we all be talking about that regardless? I might call it disempowerment tracking. Shouldn't we all be tracking our imminent disempowerment regardless of how it's implemented?
How do you look at the AI development, and what's your prediction about the future of AI?
See, I don't really know what AI does these days, you see. So you're asking me a question outside my area of expertise. I would say an area of expertise has to do with whether these devices actually do what we do. I don't think they do, because they're not conscious. I don't think they will ever become conscious by virtue of being computers in our current sense of the word. I don't know if that's an answer to your question. It doesn't mean that they won't be better than us.
Dr. Penrose is explicitly admitting that he doesn't track what AI actually does these days, and he doesn't have particular insight into what AI is ever going to do. He can just tell you whether it's doing the same thing as humans on the inside or not. And he's pretty sure it's not, because it's not using uncomputable physics. That's all he knows. So he's just admitting that his current knowledge state is potentially seriously lacking in predictive power over whether we're all about to be doomed. He's admitting that that's not his area of expertise, which I actually appreciate the humility, but it's like, okay, well, somebody certainly should be taking a look at that. Even if it's Penrose, opting out of doing that, somebody definitely should be looking at that.
The biggest risk of AI development is?
I think there is a risk involved here.
Oh, Roger Penrose is about to talk about AI risk. What does he think the risk is?
Part of the risk is people thinking that they're actually...
That there is a conscious.
They're conscious, yes. There might be an even more of a risk if they were conscious. You see, maybe one could understand what's involved in consciousness and develop some kind of device. I'm not calling it a computer, because in my view, it would not be a computer. It would be something else, some device which is conscious.
Okay, so he's identified two risks. Number one, people thinking that they're conscious when they're not. Okay, I'm not entirely sure why he thinks that's a risk. Maybe because they'll put too much faith into it. I don't know. And the second risk is, hey, maybe one day we'll build AIs that are conscious by Penrose's definition, and then who knows what'll happen. So fair enough. Okay, I understand why he would make that claim. I think that's pretty much all he says on the topic of AI risk. Now the discussion turns to his explanation of why he thinks consciousness is the special uncomputable physical process.
Since I believe consciousness is a physical process, I don't think we understand it. I think it involves the collapse of the wave function. That's partly a negative conclusion from, I don't see it anywhere else. But the collapse of the wave function is very mysterious and involves certain retrocausal things, which are a little bit puzzling. I think the way that time works is not so clear when you're talking about, but there are certain things which are in contradiction, you almost say, with ordinary causality.
Did you hear when Penrose said about consciousness? I think it involves the collapse of the wave function that's partly a negative conclusion. So he's actually, by negative conclusion, he means he's using the process of elimination. He's saying, like, consciousness is so mysterious, and when I look at all the physics around me, it doesn't seem like it would implement uncomputable consciousness. But then I look over at quantum physics, and I see the collapse of the wave function, and that to me is a mystery, and consciousness is a mystery. So by the process of elimination, the only other mystery left that I think could be mysterious enough to explain consciousness is this wave function collapse thing, especially because it's really weird to look at time when you're doing quantum theory. There's potentially retrocausality, which I'm not even sure how accurate that is as a description of quantum theory. I'm not an expert. But basically Penrose is saying, look, what else could it be? There's just nothing potent enough to explain the mystery of consciousness except something to do with wave function collapse. So I'm going to go with wave function collapse. Can I actually explain what's going on? Can I give you like a satisfying account of specific examples of people being intelligent and how that traces back to quantum collapse? No, I don't think he would claim to be able to do that. He's just saying, look, by the process of elimination, I think this is a mystery generator that we ought to look at to understand this boundless mystery of intelligence. Whereas in consciousness, from my perspective, again, boundless mystery, we just took a sledgehammer to it. We just figured out what it means to embed meaning in high-dimensional vector spaces. And, and we just figured out how to have a black box that has a certain type of architecture that sure looks a lot like the brain's architecture without any uncomputable physics, we know for a fact. And it sure is outputting things a lot like the brain. It sure is having visual hallucinations in the visual version of it that sure look a lot like human dreams. You don't think any of this is meaningful in terms of like unpacking how humans work because it doesn't have quantum collapse? I think you got to give up on this little mystery generator here because Penrose, a lot of the times, things that are mysterious turn out to reduce to non-mysterious parts. Back in the time of Lord Kelvin, one of the greatest mysteries was matter that responded to your will, elan vital, like my hand. My hand responds to my will. That used to be one of the greatest mysteries. But remember, it didn't turn out to have a mysterious explanation. It turned out to just be a long wire carrying electrical signals connected to muscles that responded to those signals. And if you wire up other matter, like artificial hands, you can get the same effect. So it turns out that this infinitely mysterious thing of why my hand responds to my will, it turns out that was made out of parts and all of the parts were non-mysterious. I think we should expect that out of intelligence and consciousness. We're already seeing it. We just saw it in our lifetimes. A philosophical mystery got resolved. The mystery of where do words get meaning. The symbol grounding problem. We saw the symbol grounding problem get solved. An age-old philosophical mystery. Like we now have a computational architecture that explains how symbols get grounded, where words get their meaning. That's crazy that we solved that problem. And the parts were not mysterious. The parts were not uncomputable. So Penrose, get with the program. Stop finding mysteries with the process of elimination. Just look at the actual phenomena. Look at what intelligence actually does, the work being done. And look at what fraction of that work we keep doing artificially. And extrapolate. Okay, so that is Roger Penrose's recent interview about AI on the This Is World podcast. What should we take away? Number one, Penrose is confident that human intelligence and consciousness relies on uncomputable physics that we haven't discovered yet because of the process of elimination where no other physics that he's found is sufficient to explain the mystery of consciousness. So this is like a major pillar of Penrose's worldview here. Number two, he admits that he's not an expert in what today's AIs can or can't do or where they're going. He doesn't seem to try to put any sort of boundary whatsoever in terms of how powerful they can grow. He's even mentioned, if I understood him correctly, he's even mentioned maybe they'll even pass the Turing test, but that'll still just be mimicry. That won't really count as true intelligence, which to me implies that he's putting a very, very high upper bound on how high even today's AIs can go without being consciousness, which to me raises the question of okay, so why are you so focused on this uncomputable consciousness thing if it doesn't even help you put a boundary on what AIs can do? I don't know. And finally, he just overall admits to not having a functionalist account of intelligence. He just doesn't concern himself much with input-output, with what can intelligence do, what can intelligence not do. He just has this theory that humans work a certain way. They have this mysterious uncomputable consciousness. And he likes thinking about this theory, and he doesn't like going off and thinking about the limits of intelligence. It's just not a subject he concerns himself with. It's not his thing. When he's asked to talk about AI risk, he gives a super vague answer, and he says, yeah, maybe one day people will build AIs with the same architecture that the human brain is built with and tap into the same physics. That's all he says. He's super vague about the whole thing. It just seems like he has this one hobby horse. He loves studying the physics of it. He loves connecting it to quantum theory, but he's totally disconnected from the actual discussion of like, what capabilities does AI have today? What capabilities might it have tomorrow? When might it be 100 times more powerful than the human race? He's just not part of that discussion. He's just off in his own world, making his own connections, making highly questionable claims. Oh, and the last takeaway, he's heavily influenced by Gödel's freaking theorem. He thinks that a theorem about formal systems, when they really have no choice, when you put them in a catch-22 and they just say, okay, we're not going to prove something one way or the other, for him, that's this super profound thing that proves to him that humans must have some extra special, uncomputable thing that a formal system like a computer could never have because of Gödel's theorem, which in my mind, if you go back and listen to my explanation, is just nonsensical. Like he's just totally misinterpreted the implications of Gödel's theorem. Which is crazy for me to say because the guy is obviously brilliant. He won the 2020 Nobel Prize for figuring out that black hole formation is consistent with the predictions of the theory of relativity. My name hasn't come up in any year for the Nobel Prize so far. So he's definitely ahead of me on that front. He's definitely a very smart guy. And yet, the arguments that I've made against him during this episode, I don't think I'm speculating. I think I'm on very firm ground here. And also, I think I'm representing the mainstream here. It's not like Penrose has like a big faction. He is very much in the minority. The Gödel view is a little bit less minority. Like you're probably going to find more people who think Gödel's theorem is a significant difference between humans and machines, even though I think that's totally misguided. That view is a little bit less minority, but his view about consciousness using uncomputable physics is very minority. As far as I can tell, his camp has just really not attracted any supporter I've ever heard of. Like I couldn't personally name a single supporter of the microtubule uncomputable consciousness camp. It's like just him by himself for many, many decades. So it's a crazy situation. And it's representative of the larger reason why I'm doing Doom debates, which is like, we got the smartest people in the world here. The kinds of people that humanity depends on to point out AI doom, and they're just not. They're just not doing their duty as humanity's smart people. And so a random podcaster like me has to be the one sounding the alarm. I don't know why, but it's like, some of us do see this, okay? I know Penrose just doesn't think this is even a topic for focus or discussion, but I do think AI is becoming super intelligent. I don't think it needs uncomputable consciousness. I think it's getting very close to ending and disempowering humanity, and I just wanted to sound the alarm, and I'm sad that people like Penrose, who our species really should be able to count on to get on the same page, just clearly will go to the grave without being on that same page. I think that's sad, and I think that's a big reason why P-Doom is high and why our species doesn't look like it's going to good places. Thanks very much for watching. I hope you have a great weekend. Please smack the subscribe button on the channel. It really helps grow the show so we can attract better guests, so we can make a bigger impact on the discussion. I appreciate it, and I'll see you on the next episode of Doom Debates.